So let's now see how we can write a composition of two permutations, each of them written as a product of disjoint cycles, as a product of disjoint cycles. So let's do an example. Let sigma and tau be two elements of S7. So S7 is the group of permutations of the set 1, 2, 3, 4, 5, 6, 7. And I'm going to take, for my example, sigma to be 13524 and tau to be 147236. Just so that we keep our eyes on the ball, before I compose them, let's make sure that we actually understand what this notation means. So here's sort of a side note. What is sigma of 2? What does sigma do to 2? Remember, sigma is a function, right? It looks like just a bunch of numbers here, but it's a function. It's a permutation. So what does sigma do to 2? Sigma maps 2 to 4. So it's 4. What does, say, sigma do to 5? Well, sigma maps 5 to 1. Right? Similarly, what does tau do to 4? Tau maps 4 to 7. What does tau do to 5? Well, I cannot find 5. What does that mean? That means that tau maps 5 to itself. Okay? And just to make sure that you understand it 100%, I recommend you write down what sigma does to every one of the 7 elements that are in the set 1, 2, 3, 4, 5, 6, 7. And it's the same for tau. Okay, so now we want to compose them. So let's compose sigma and tau. Remember, this is still in S7, right? So in other words, sigma composed with tau is still a function, it's still a bijection from the set 1, 2, 3, 4, 5, 6, 7 to itself. 1, 2, 3, 4, 5, 6, 7. Again, just sort of as a side note, let's compute what this does to some elements. And then we'll actually write it as a cycle notation. So let's start with 1. Let's see, what does it do to 1? So that's composing things, right? So first the composition always starts on the right. So what does tau do to 1? Tau maps 1 to 4. So tau of 1 is 4. So this is just sigma of 4, right? Tau of 1, tau maps 1 to 4. So tau of 1 is 4. What is sigma of 4? What does sigma do to 4? 4 is mapped to 2. So that's 2. So sigma composed with tau of 1 gives you 2. One more maybe. Sigma composed with tau of 3. What does tau do to 3? It maps 3 to 6. So that's sigma of 6. And what does then sigma do to 6? Oh, nothing. Sigma just fixes 6 because 6 is not there. So it's 6. Okay. So now the goal is to write it as a product of two. Product of disjoint cycles. I don't know, there's going to be 2. Sometimes it can be more than 2 cycles, right? Like you saw in an example here. All right, so I'm writing it like this. Sigma composed with tau is, all right, so sigma goes here. That's 1, 3, 5, 2, 4, 1, 4, 7, 2, 3, 6. Okay, right? That is here. That is sigma, and that is tau. That's a 6. Doesn't look like a 6. It's a 6. Okay, so what did I do here? Well, I was just sort of writing this composition, plugging in a number, and first I was sort of looking from the right to left, right? What this function on the right does to it, and then what the function on the left does to it. So I'm going to exactly do the same thing here, except I'm going to work with cycles. So I know that this is a permutation, so it can be written as a product of disjoint cycles. How do you write the permutation as the product of the joint cycles? I already told you. So you start with the lowest number that isn't fixed. What's the lowest number? 1. Okay, so I want to know what this gigantic guy does to 1. I go from the right, yeah? So, well, this doesn't do anything to 1. There's no 1. Oh, here, there's 1. So tau maps 1 to 4. So I need to now check what happens to 4 under sigma. So I'm here. So 4 is mapped to 2. Again, so I start with 1. 1 isn't fixed apparently. So I go from the right. No 1 here, there's 1 here. So 1 goes to 4. Now I'm looking for 4. There it is. 4 goes to 2. If there were more permutations here, I could even look now where 2 goes. But there's no more 2's. So that means 1 went to 4, 4 went to 2. So under decomposition, 1 goes to 2. Right? Just gonna write it above here, but just for this 1. This does nothing to 1, and this one sends 1 to 4. And I'm moving left because composing function always goes from right to left. So and this one moves 4 to 2, and this one does nothing to 2. So altogether 1 goes to 4, 4 goes to 2. So from this, right, I get that 1 goes to 2. So 1 goes to 2. All right, let's continue. So now I need to know what happens to 2. From the right, there's 2. 2 goes to 3. No 3 here, no 3 here, here. 3 goes to 5. So 2 goes to 3, 3 goes to 5. So altogether 2 goes to 5. Now I need to know what happens to 5. Okay, start with 5. No 5 here. You're going from right to left. No 5 here, no 5 here, no 5 here. There's 5 here. What happens to 5 here? 5 is at the end of the cycle, so that means it's mapped back to the beginning, so it's mapped to 1. Also 5 goes to 1, so that means I'm closing my cycle. So I get 1, 2, 5. All right, what do I do next? I'm taking the lowest number that isn't here and isn't fixed. Let's try 3. I'm going to put a 3 here so I remember what I picked. If it's fixed, I'm going to erase it. So from the right, okay, there is 3. 3 is mapped to 6. No 6 here, no 6 here, no 6 here. That's it. 3 is mapped to 6. Now what happens to 6? From the right. 6 is mapped to 2. I need to look for 2. There it is. 2 is mapped to 4. I need to look for 4. No more 4s. So 6 is mapped to 4. What happens to 4 now? No 4 here, going from the right. No 4 here. 4 is mapped to 7. Looking for 7 now. No more 7s. So 4 is mapped to 7. Finally, what happens to 7? Well, I know this must be the end, right? Because I already used up all the 7 elements and it's a bijection, so that must be the end. But sometimes it's good to do this last step to check that you haven't made any mistake. So 7 should go to 3. Let's check. So no 7 here. There's 7 here. 7 goes to 1. Looking for 1, no? No 1 here. 1 goes to 3. Oh, so 7 goes to 3, just as expected. Okay, that's sigma tau. Let's check that we actually get these 2 results, right? So if I apply this, this thing here to 1, so 1, 2, 5, 3, 6, 4, 7. If I apply this function, this is a function, right? This is a function. This is this. This is sigma composed with tau. To 1, what do I get? 1 is not moved here. 1 goes to 2, so it's 2. Ta-da! All right, the same thing. If I do it to 3, I should get 6, right? So let's do that. 1, 2, 5, 3, 6, 4, 7. Applied to 3. What do I get? 3 goes to 6. No more 6s here, so it's 6. Ta-da! Yeah, it all works out. Okay, well this tells you what happens to any element. All right, let's do it in the other order. So if I do tau composed with sigma, what do I get then? So that means I'm writing it the other way around. So first goes tau, and then goes sigma. right? This is sigma, and this is tau. All right, and again, I'm going from right to left, starting with 1. Where does 1 go? No 1 here, going from right to left. 1 goes to 3, looking for 3. 3 goes to 6, no more 6s. So 1 goes to 6. Now 6. No 6 here, no 6 here, here's 6. 6 goes to 2. No more 2s. So 6 goes to 2. Remember, things at the end of the cycle always go to the beginning, right? Things anywhere in the cycle always go to the next thing on the right. So 1 goes to 3, 3 goes to 5, but if you're at the end of the cycle, you go back to the beginning. Now what about 2? 2 goes to 4, looking for 4. 4 goes to 7, so 2 goes to 7. Looking for 7 now. No 7, no 7, no 7. 7. 7 goes to 1. Oh, 7 goes to 1, so that means I'm closing my cycle. Next one. Smallest number that's not in the first one, that's 3. What happens to 3? 3 goes to 5. Looking for 5. No more 5, so 3 goes to 5. What happens to 5 now? No 5. 5 goes to 1. No 1, no 1. 1 goes to 4. I know this must be the end, right? Because I already used up 7 elements. But let's check that 4 really goes to 3. 4 should go to 3. So 4 goes to 2. Looking for 2. 2 goes to 3. Yeah, okay. It all works out. Important thing to notice. We just evaluated this, right? 1, 2, 5, 3, 6, 4, 7. We evaluated it at 1. And we said we got 2. What happens if I evaluate this at 1? 3, 5, sorry. 1, 6, 2, 7, 3, 5, 4. Evaluated at 1. Oh, I get 6. I don't get the same number. I have 2 functions, and they give me 2 different values on a given number, so that means they're not the same function. So from this, right, from this I see that sigma composed with tau is not equal to tau composed with sigma. In particular, S7 is not reducible. So here's another example of a non-abelian group for you. In fact, except for S1, which is trivial, and S2, all the other symmetric groups are non-abelian. Okay. Why did I do that? To see that these two are not the same, rather than just look at them. I mean, this is 1, 2, 5, 3, 6, 4, 7. This is 1, 6, 2, 7, 3, 4, 5. Don't I see that these two are just different? So I already know that sigma composed with tau and tau composed with sigma are different elements? No, because it is possible sometimes to write the same permutation in several different ways using cycle notation. So let's just write this down here. So note, or caution, maybe caution. It is sometimes possible, usually in fact, I mean it's, yeah, let's just write it as usually possible. I mean, except for trivial examples, it's always possible. It is usually possible to write a permutation as a product of cycles in more than one way. Example, these three cycles actually represent the same permutation. Really? Let's look at this. Under this one, 1 goes to 2, 2 goes to 3, 3 goes to 1. So 1 goes to 2, 2 goes to 3, 3 goes to 1. What about this one? 2 goes to 3, 3 goes to 1, 1 goes to 2. That's exactly the same cycle, just written in a different order. Under the first one, where does 1 go? 1 goes to 2. The second one sends 1 to 2. The first one sends 2 to 3. The second one sends 2 to 3. And the first one sends 3 to 1. And the second one sends 3 to 1 as well. So you can always cyclically permute these elements inside and you get the same permutation. So a word of caution, right? Just because a permutation looks different when written using cycles doesn't mean that's actually a different function. To check that two functions are different, well, sort of by definition, you have to find an element when, if you evaluate these two functions in that element, you get two different answers. Which is what we did here, right? We evaluated these two permutations on element 1 and we get two different answers. And so I know that these two functions cannot be the same. Okay. There is something, let's look at now the orders of various cycles. So for this, let's first define what's the length of a cycle. So let A1, A2, AN be a cycle, then N is defined to be the length of it. The length of it, i.e. it is the number of elements in the cycle. Right, so for example, 1, 3, 5 is of length 3. 1 or 4, 7, 1, 3, 2 is of length 5, and so on. So the claim is the following. So a little proposition here. Let sigma be a cycle of length n. Then the order of sigma is n. So what's the order of a cycle? Well, that's how many times I need to compose it to get to the do-nothing cycle, so to get to the do-nothing permutation. Why is that true? First, let's do an example, and then we'll do it in general. So let's look at this example. So let's look at the cycle 1, 2, 3, 4. That's a cycle that can be thought of as an element of S4. So let this be sigma, and now let's try to compose it. So sigma squared, that will be 1, 2, 3, 4, 1, 2, 3, 4. All right, and now it's not only important to actually do the calculation and see what we get, but to sort of methodically see how this works. So I start with 1. And so here I'm going to just maybe write this diagram next to the first cycle. So it's 1, 2, 3, 4, right? And you go like this. This is sigma. And now I want to know what happens to sigma squared. So that's going to be in blue. So 1 goes to 2, and then 2 goes to 3. So 1 goes to 3. Okay? So essentially you just skip the 2. So that would be sigma squared. What happens to 3? 3 goes to 4, and then 4 goes to 1. So you just go back to 1. Okay? Now what happens to 2? 2 goes to 3, and then 3 goes to 4. So 2 goes to 4. Okay, and then the 4 will go to 3. So 2 goes to 4, and then 4 goes to 3. What was happening here as I was composing these elements. Normally, in this cycle, each of these numbers goes to the next one. But if I do it twice, then this one goes to the next one, and then this also goes to the next one. So altogether, I go 2 steps to the right. Let's do sigma 3, and you can already imagine what's going to happen. Now you're going to go 3 steps to the right. I start with 1. I'm not going to use the diagram anymore, but you can imagine you're going to go 3 steps to the right. Why? Because here 1 goes to 2, 2 goes to 3, 3 goes to 4. So first time you do it, you go 1 step to the right. Second, because every time you apply this, it tells you move 1 step to the right. So if you apply it 3 times, you move 3 steps to the right. 1 goes to 2, 2 goes to 3, 3 goes to 4. So 1 goes to 4. What happens to 4? 4 goes to 1, 1 goes to 2, 2 goes to 3, so 3. And finally, 3 goes to 4, 4 goes to 1, 1 goes to 2, 2. And, alright, maybe the most instructive thing is to see what happens if you do it 4 times. Although you already expect what's going to happen. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. You move 1 step to the right, and because you have to do it 4 times, you just go back to whatever you had. So that's 1, and the same thing is going to happen to 2, 3, 4. But as you know, we don't write these 1 cycles, so that's the identity. So, how do you prove it in general? Well, the same way. So, let's prove the proposition here. I'm just going to sketch the proof. So, let sigma be a1, a2, an. Okay? And now what happens if I compose sigma with itself? What do I get? So I'll start with a1. a1 goes to a2, and a2 goes to a3. So I get a3 here. What happens to a3? a3 here would go to a4, and a4 would go to a5, and so on. Right? There might be another cycle here to start, but let me just put dots here. What was happening to the numbers here is now happening to the indices here. So, in particular, applying sigma n, let's just look at it, what happens to a random element now. So sigma, let's see what happens to a1, okay? That's sort of the easiest thing to understand. So sigma of a1 is a2. Sigma squared of a1, well, sigma moves a1 to a2, and then a2 gets mapped to a3, so that's a3. Sigma cubed of a1 is going to be a4, right? Because sigma is going to map a1 to a2, then again a2 to a3, and then again a3 to a4. So you get that sigma to the s of a1 is as plus 1. Well, okay, that's true if s is less than n. If s is equal to n, then of course you wouldn't get an plus 1, you just go back to a1. So, because all these elements are distinct, that means neither sigma, nor sigma squared, nor sigma cubed is the identity. You actually have to go to sigma to the n to eventually send a1 back to a1. So this already shows you that the order of sigma is at least n. because you needed n steps to map A1 back to A1. But, so why did I choose A1? Because that's sort of the easiest thing to see what happens to it. But you can just as well look at now what happens to, say, A2. And sigma of A2 is going to be A3. Sigma of A3 is going to be A4. And so on. So it's the same exact thing that's happening, right? Sigma to the S of A2 would be sorry, this was sigma squared. Right, so okay. Sigma squared of A2. So it's a S plus 2. So if S is less than n minus 1, then what happens if I apply sigma n minus 1 to A2? Well, I get A1, and then sigma n of A2 is equal to A2. So again, you go back to the original element. So you do this with every single one of these elements. I mean, you can sort of make this completely formal and write what happens to AI. You just have to be careful how to get the index correctly. And so anyway, you get that proposition that a cycle of length n has order n.